Hey guys, Mr. Tima here. I'm going to go through impulse and momentum. Now, this is a pretty big chapter, so I'm going to go kind of quickly. Feel free to go back and listen to things again if you need to. But here we go. So, impulse and momentum, right? There's your assessment statements. So, momentum, and hopefully you've watched the video. You should have watched the Understanding Car Crash video, which will help you out a lot with this. But momentum, which is rho, and I don't know why they use rho, but it's this P, rho, equals mv. Okay? The difference between momentum and inertia is based upon mass, momentum is based upon the mass and how fast something is going. So this is the whole idea that, yeah, a small bullet is a big deal going super fast, other than that little thing going really slow. Okay? So what has more momentum? An object with a large mass and a small velocity, slow moving train, or a object with a small mass and a large velocity, a speeding bullet? Well, it depends, right? It really depends. Okay, they actually could have the same. So, for example, if we look at it mathematically, which has more if you will, okay, the 10 kilogram moving at 1 meter per second and the 1 kilogram moving at 10 meters per second would both have a momentum of 10 kilograms per meters per second. Okay, so it's the same thing. This is a real quick example problem. See if you can figure that out, and we'll be right back. Hopefully you looked at that and you figured it out, and the answer is, there we go, to move my little answer document right there. Hopefully you saw that the answer is 56,000 kilograms per meters per second. And remember, to the right, or east, if you will, or to the right, because it says up there to the east. All right. And that would be your answer. Okay. All right. So think about this. We have a egg falling, hitting a plate, and an egg falling, hitting a pillow. It's dropped from the same height. One breaks, one doesn't break. And you should have seen this explained in. You should have seen this explained in the video. All right, but if you want, you can click right here on the notes in the traditional notes and watch it again. But the whole idea is this idea of impulse, this idea of allowing something to slow down, giving it time to change. So, impulse literally means a change in momentum. It can be a change in direction and in force. And here's our equation, okay? I know that's kind of broken out there, and you're sitting there going, well, how are we going to use this? Okay, an impulse is measured in newtons per second, okay? And impulse is a vector quantity. So let's talk about that. So here's our situation. We have a car. We have a car that's going to hit a brick wall, and we have a car that's going to hit a haystack. Well, let's look at impulse. Well, first of all, if we understand this idea of F equals ma and we substitute in our stuff, our impulse equation is F delta t, so some force over some amount of time, equals the momentum. All right, so for example, if we give these numbers right here, it says if it's a 100 kilogram car in both situations and they're both moving at 60 meters per second and they hit, they're going to hit with the same force. The difference is, all right, the difference is if we substitute the numbers in, sorry about that, these are kind of out of order. If we substitute our numbers in, we'll notice that what if it only takes 0.01 seconds for the car to hit the wall, okay? And it takes 10 seconds for the car to hit the wall. Well, if we look at that, or excuse me, if it takes 0.1 seconds for the car to hit the brick wall and it takes 10 seconds for the car to come to stops after hitting the hay, our momentum is the same in both cases, but our impulse isn't. Our impulse isn't. The impulse for the car hitting the hay is actually 600 newtons because you're dividing it by 10. But the car that's hitting the brick wall, since it stops so suddenly, it actually feels or experiences a force or an impulse of 600,000 newtons. That's why most people don't survive a car crash hitting a brick wall, but they can with like hay and stuff like that. So, the highest person ever to survive falling out of a plane was a guy that fell 7 kilometers or 4.3 miles during World War II. He would fall about 2 minutes before he hit the ground. How did he survive? Okay, well, how did he survive? So basically, I put this on here because if you basically fell from up here where basically Scioto High School is right here. If you would, that would be like falling from Scioto High School all the way down to the Ohio State Airport. Okay, well, how did he survive? Think about that for a second. Take a guess. Well, it was actually the choice of he actually hit on the side of up there in the Alps up by Switzerland, and he actually hit on the side of like a mountain where there's a bunch of snow, and the snow it took him a while to slow down. So that snow as he fell kind of slowed him down. Now, luckily, he finally rested or fell next to like this person's like hut or their small cottage, and they were able to like nurse him back to health. All right, let's try this impulse problem. So again, you're going to use that Ft equals mv. Ft equals mv. Take a second, see what you can get there. All right, and that should be your answer right there. 70,000 newtons to the east. Okay, so it's mass times velocity divided by 0.03. And again, if you have questions on these, make sure you ask during class and we'll be ready to go. Momentum, again, is a vector quantity. Sorry about that. So again, if we have force over some amount of time, we can just take the area underneath to calculate impulse. So again, here's our impulse equations. And you can transcribe, there's our impulse. If momentum's this, then really impulse is equal to momentum. Pretty simple. All right, so collisions, and this is where we're going to kind of go pretty quick, but again, something we need to understand. So momentum, the momentum before has to equal the momentum after. Pi initial, momentum initial equals momentum final. Always, 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 always. So, for example, if we have exactly the same velocity, okay, and exactly the same masses, then when something hits, they technically stop. But what if this guy, maybe you've ever done bumper cars, if these guys had a zero velocity and a mass, had the same mass over here, but they have a really big velocity, okay, I'm sorry, not zero velocity, but a little velocity and a large velocity, then what would the result be? Are they going to go to the left or are they going to go to the right? Take a guess. Well, they're going to be going to the left because these guys, even though their masses were the same, their velocity was greater. Okay, so this one's going to experience a bigger force going to the left, and they're going to move to the left. Okay, so our first type of collision is elastic. When you hear elastic, you should be thinking like a rubber band. Okay, you should be thinking like a rubber band. Okay, so here is the equation, and it's really not that hard. It's m1 v1 of initial of the first thing plus m2 v2 of the second thing equals m1 v1 of the first thing plus m2 v2 of the second thing. So this would be like somebody hitting a hockey puck, the curling videos we've shown, pool, just in general. To give you a look at what that looks like, it looks like this. So if a ball is coming, it bounces off. Elastic, that snapping, that snapping. Here's a little thing, all right? A little bit of a hit there, okay? So if we did this, let's pretend that we were doing a problem here. It says a curling stone of 19 kilograms was thrown traveling at 4.5 meters per second when it has an elastic head-on collision with a squirrel that has this mass at rest. So let's think about that. M1, V1. M2, V2. V2 would be 0. Very good. Find the velocity of the squirrel after the collision if the stone is traveling at this. So remember, if M1 is the stone, its M didn't change, right? Its mass didn't change. The squirrel's mass didn't change. M2 didn't change. But the initial velocity of the stone, M1, V1, and now we have the stone, this would be M1 would be 19, but V2 is now 1.5. Okay? And then the squirrel, we got to find that new V. If you do that, you should find this answer right here. You should find the answer of 24.7 meters per second as That would be V. That would be squirrel V2, and we can work that out on the board if you need me to do that. The second, so we had elastic, now we have inelastic. So inelastic is when you have mass 1 V1 plus mass 2 V2, just like before, except now they are kind of stuck together. This is the classic football hit where some guy is tackling another guy. So they both have a different mass and velocity, different mass and velocity. Then when they make the tackle, when they grab each other, they become one new larger mass moving at some velocity together. In hockey, you see people kind of join up and slam into the boards together. Okay. So in outer space, we can see this, right? In outer space, we could see our guy coming here, and then like a big fish eating a small fish, whoop, they become a new mass. They become a new mass. All right. Kind of look at those for a second. We'll watch the fish eat them one more time. Gone. All right. Good old thing right there. They kind of move like that. Check out the numbers real quick. Okay. If you notice, okay, the velocity of the train was much faster, but now they have the same velocity, but since they have different masses, their momentum has changed. Okay. Down here, the same thing happens. They end up having the same velocity. Okay. All right. So again, this would be our little ball moving together. Okay, so here's our problem with this one. A running back has this, a safety has a mass of that. So there's your two M's. It's going to be your total mass on the right side of the equation, but it's also going to be your masses, mass 1, mass 2. And they were traveling at this. If after their collision they were both traveling at this, what was the running back's initial velocity? Again, you're just looking for that one missing V on the left side of the equation. Go ahead, try to figure that out, pause for a second, and then come back. And you should have found that to be 2.71. And remember, positive and negatives are very important here. Again, we can solve that one out on the board if we need to. All right, last one is an explosion equation. And you shouldn't freak out about the explosion equation. The explosion equation is actually just the opposite of the inelastic. Inelastic is coming together and sticking together, and the explosion equation is actually when you're already together and you're kind of blowing apart, if you will. Okay, so what would that look like is two things stuck together or one object stuck together and then breaking apart. Okay, the thing is, what if they're different sizes? What if something, this happens a lot, what if something's really small and something's really big? Well, when they leave, the smaller one's going to leave at a higher velocity. Okay, if you've ever messed around on a raft in a pool, or if you've ever been on like a little rowboat in a lake, or if you've ever been on one of these diving rafts as they're called out there in the lake, you know when this guy jumps off, he's going to jump, but the raft's going to move back a little bit. Now, if it was a dock strapped into the ground, you get a nice jump off of here because this doesn't really move very much. But if they both move, you don't get to jump as far because some of your force and energy and momentum has been shifted backwards. Again, here you go. We have a little skateboard problem with Bart Simpson, who's Mr. Ellis, if you will. And here is your answer of negative 50 meters per second. So make sure you're able to get that one. And if you don't, make sure you ask a question about it. Again, just want to make sure that you understand that these things can happen as vectors. If they come in, they're going to hit, they're going to leave at right angles. All right, boom, most car crashes. This is actually how police officers figure out who's wrong in a crash, is they can actually look at how they deflect. Okay, if the blue car was traveling, now notice they're both the same mass. Okay, they're both the same mass and they're both traveling at this slightly the same velocity. Okay, if the blue car was bigger, then it would push the red car farther to the right. If the red car was bigger, it would push it farther north, if you will. Okay, those videos we've actually already watched. So collision review. What kind of collision would this be? What kind of collision would this be right here? Before, after. So before they're separate, after they're moving together. That would be, take a guess. Very good. That would be an inelastic. Inelastic. They stick together. They're in it together. Inelastic. Inelastic. Sorry, I went back up here. These two are together. They both hit and they both are taking off. They bounce off each other. This would be elastic. Okay. And right here, before one thing splits apart, that would be an explosion equation. All right, making a connection really quick. We kind of talked about this already with Newton's three laws, but the idea is if we have a rocket in outer space, how does it move if there's nothing for it to push off of? Well, there's an explosion back here, and we have an explosion, the momentum of the gas. But remember, the momentum of the gas this way is the same momentum of the gas to the right. And when that happens, this cone forces that force towards the rocket and allows the rocket to move. Okay, you got some book problems here to do, and you're going to have a worksheet to do as well. So again, I know those were kind of long. And again, if you need help, make sure you ask, ask, ask. All right, everyone else, Teamatron out.